I can't even begin to tell you how I'm feeling right now because working for Microsoft for over 26 years, being in the SQL community that long, I'm completely blown away by all of you that have organized this and everyone online that has taken their time, wherever you are around the world, to watch this. For me, at Microsoft, SQL Server internals is kind of my roots. So I used to be in support team back in the day for 20 plus years, and I got a reputation within Microsoft and outside of Microsoft of understanding the internals of SQL Server. And it was, quite frankly, a necessary part of my job. I had to understand how things worked because I found myself troubleshooting the most complex problems in the world. Found myself connecting to people with like Robert Dorr and Slava Oaks and all the people in the SQL engineering team, using techniques like debuggers and all sorts of things, but also understanding the source code. So a lot of times I do these presentations in various places on things like latches and memory and I/O and so forth. And a lot of it having to do with researching things in the source code and trying to explain these things in a way that pretty much anybody could understand. Although, to be candid with you, a lot of people would come to me after these talks and say, hey man, my brain was melted. I didn't understand anything you said, but I loved it, man. Put the thumbs up to me. And I'm shaking my head going, okay, all right, well, I guess I'll keep doing those things. So the last few years, maybe you've seen me out there in the community at a physical event or now in virtual events, and I am not doing much of that anymore. And so one of my colleagues mentioned about this conference, and I talked to Anthony, who was a tech reviewer for my first book, and I said, hey, do you guys think memory would be a good one? And Anthony's like, yes, that would be a good topic. Please submit that, right? So I submitted this topic, and I hope you'll enjoy this session. I'm not sure I can live up to what you're going to see later. So maybe we'll start maybe not as deep as these other topics, because I think Joey put insanity, and then for Argenis to be the last one of the day, heaven help us all. So we'll see how that all rocks. So let's talk about some memory. First of all, a couple of things. Number one, I have already put this deck on this website, aka.ms/bobwardms. Although, before the end of the day, I will put my deck and scripts for my demos and so forth up on the 8KB GitHub site. I haven't put it up there yet. I was working on this last night. But if you want the deck right now, you can get it on this site, aka.ms/bobwardms. And what's interesting about that site, if you go look at it, there are presentations I've done for the last decade out there, including some internals on various topics. So let's dive into what we're going to talk about today. This is kind of what we're going to do in the next 75 minutes. And what we're going to do is we're going to go through a bit of this. My moderators, Hamish and Ree, will probably stop me about halfway through or so. We'll see if there's any burning questions you have out there, and then we'll proceed to the end of the talk, and then we'll end up with some questions as well. So we're going to talk a little architecture. We're going to talk about how you can make some configuration choices and how you look at what I call memory accounting. How do you look at this data to decide what memory looks like for SQL Server? We're definitely going to talk about dynamic memory management. Hopefully I'm going to bust some myths about how that works in SQL. I got some other memory topics I'm throwing in there. I also wanted to cover at the end of the topic a little bit about how does memory work slightly differently in Linux containers and Kubernetes. And then you might find interesting the last slide I have and a small little demo about what have we done in Azure to be a little bit different than we've done with SQL Server. It's pretty much the same, but there are a few interesting nuances. So let's just go into the topic. So this is my world of the SQL Server memory architecture. Now, what I'm not going to do today too much, but I'm going to be able to help myself, is it's all about APIs. The SQL Server engine is a Windows program, and it uses Windows APIs to allocate memory. But it does something in a very interesting way. So let's kind of dive into what are the major components of memory that we allocate for use of SQL Server. So first of all, we have something called caches. Let me back up one here. So we have something called caches, that's in the blue, and something called fixed memory. Now you recognize some of these names: the buffer pool to store database pages, plan cache to store stored procedures and text parameterize queries or queries that we've compiled and put into plans. We have other caches and pools that we store things in, and we have column store, which is stored in the form of pools and also participates with the buffer pool. So that's what's in blue. What's unique about caches, and we're doing all the allocation of memory for these things, is that they can grow, they can shrink, and here's what's unique about them. There's a backing store for them. For example, as you know, the buffer pool is backed by database pages on disk. The plan cache is backed by the actual stored procedure text that is stored in system tables. And column store Everybody kind of thinks column store is an in-memory technology. And don't get me wrong, it's fastest when it's all in memory. But these are compressed indexes that are stored on disk as well. So the thinking here, just like maybe a swap file or something, this is memory, SQL's allocating, but we can shrink and trim this really, really low because everything's on disk if we have to load it back into cache. Now, fixed memory is different in this gray area. It doesn't take up near as much space typically, and I've kind of drawn this diagram to show you what is typically your biggest consumers of memory in SQL Server. And so fixed memory can grow and shrink, but it only can shrink when it's not used. So an example here is connection memory or memory grants we use for like hashes and sorts. So it's not used, we can get rid of it, and it can grow, but it cannot shrink when it is in use, unlike these caches. These caches, if they're in use, like a database page, if it's what's called clean or not dirty or changed, we can just free up that memory and give it to somebody else. If it is dirty, what do? We write it to disk, we flush it, like Lazy Writer can flush this, and then we can give that memory to somebody else. But you can't give connection memory to another connection because there's no way to have a backing store for it. There is no disk behind connection memory. Now, typically we use something called a memory object. Memory object is a abstraction in the SQL engine that the SQL OS component gives other developers on how to access memory. So that's caches and fixed memory, and you're going to find, it's very interesting, that if we don't have enough memory for our fixed memory, you're going to run out of memory inside SQL Server, but it's going to be a little bit different than you might expect. So another thing you need to know about SQL Server memory is something called overhead. SQL Server is an executable, and therefore there are things inside the normal nature of running an executable like thread stacks that take up memory in the SQL Server architecture. Well, why am I saying that? That's because between fixed memory and overhead, again, if we run out of memory, we have to make sure that SQL's memory exists just for that. But also, when we talk about a concept called locked pages, the SQL Server overhead can actually be swapped out to disk, which is really kind of crazy, and SQL doesn't know it, and that's when you get into a really bad problem called working set trim issues. Now, finally, I want to dispel some myths about hackathon memory or in-memory LTP. So in-memory LTP is fixed, but and I say fixed for this very reason. Think of in-memory LTP as almost like a dynamic disk drive in memory for data, because this is where you store your data for memory optimized tables, and that data has to fit in that space. So hackathon memory can grow, but we limit it. We don't let the entire, notice it doesn't take up the entire SQL chart here. So it grows, but it has limits. Now here's the interesting part. It can't shrink if there's data in it. So if you populate this thing with data and you haven't deleted that data, we cannot shrink this memory. So it's another kind of almost fixed memory that could cause you to run out of memory. Well, how do we reclaim this memory? Well, you got to delete data, and we use a garbage collection process. So for example, if memory pressure comes into SQL Server in this diagram, all the blue guys can adjust themselves, right? Because they're caches and they have backing stores. The gray fixed memory cannot adjust itself, neither can SQL overhead, and hackathon cannot adjust itself either unless you reclaim that data by deleting data, and garbage collection will kick in. So that's a little interesting look at the architecture, and we'll talk about how dynamic memory affects all of these things. Okay, so what about paging and SQL Server? I get this question all the time because people try to understand the difference between locked pages and not locked pages and so forth. So just like I talked about in the previous diagram, SQL Server has the ability to do its own paging, like almost a page file in an operating system. So for example, if we get memory pressure, we can take buffer pool database pages and write them to a database file. You know how that works. If it's dirty, if the page has been changed, we can write it and write all the log records. And if the procedure cache has pressure, and we'll talk about this concept called a planned cache eviction. That's what you call when you get rid of plans from cache. We obviously can just reload these from system tables. So you don't lose any data. That's the idea about being paging. But then again, this connection memory is not pageable. Now, Windows as an operating system, and Linux has the same concept, it can page out any process's memory, period. Doesn't matter about SQL's paging concept. And in fact, Windows can go through this process of doing this, and in some cases, SQL doesn't know it's happening. So Windows would write out pages for a process to the page file, and then there's this really crazy process called a working set trim. This was a really bad scenario that can happen. And even that SQL Server overhead for thread stacks could get written to the page file in that case. Look at that. Look at the comment in bold here. SQL still thinks it's all in RAM. So normally when you're looking at a problem for paging of SQL right here, you're looking at things that might give you
Is audio cut out for anyone else?
Yes.
Okay. Bob, if you can hear me, we can't hear you.
Whoops.
Okay, everybody in the chat, we know you can't hear. We're working on it.
Bob is muted. Oh.
Hello?
You there, Bob?
Hello?
There we go.
Yep.
Can you hear me now?
Yeah.
Yeah, you left off at still thinks it's all in RAM.
Okay. Sorry, guys. Don't know. Welcome to the world
Computers.
of virtual presentations, right? Haven't had that happen with my headset before. Okay, so as Anthony was saying, right where it says SQL thinks it's in RAM, remember this from a performance perspective. SQL doesn't know this. It just thinks everything's fine. You normally used to looking at things from a performance perspective, that things I/O related are happening that could show paging for SQL going on, but for Windows. So how do you know this? Well, you can look at things like process working set and memory pages out per second from a perfmon perspective to see if that's happening. Or look at the working set data that SQL shows. Now, having said that, SQL, after a while, we got tired of these problems in support. And so I told the engineering team back when I was in support, you got to do something about this. So we did put some logic in the server where we recognize if a severe working set trim is happening, and we generate pressure into the engine to tell itself, hey, this working set trim is happening here. You guys need to react to this. And we dump something in the error log. But typically, SQL doesn't know this is going on. So why does that even really matter? So let's go to the next screen here. Okay. We'll talk about locked in a second, why that matters. So first of all, I want to talk about some memory configuration decisions that you may be making with SQL Server. Let's bust some myths here. Number one, SQL has something called a memory model. And the default is called conventional, and we'll use the virtual alloc APIs from Windows if conventional is the model, which is the default again. So along comes the need because of these working set problems that we'd run into before, and we had just some really bizarre behavior across the years with SQL Server, where literally Windows would do this working set trim, and there was a lot of physical memory on the computer at that point available. So we didn't understand why that was going on. So this lock pages concept comes along, and you have to have the lock pages memory privilege set for the account for SQL Server. If you set that, and we're running standard to enterprise edition, we will use what's called the AWE APIs, address window extension APIs. When we do that, and we use those APIs, Windows cannot trim that memory. It's considered locked. Now, what does that even mean? What it means is that it doesn't even look like it's part of the working set of a process. When you use these APIs to allocate your memory instead of virtual alloc, the Windows operating system doesn't even know that's part of your working set. Therefore, it can't trim you, which is why we use this technique. And I often tell customers in many cases that this is something you should be using in your environment because of that type of problem. And if you don't know, you can go back and read a little bit of the history of what AWE is all about. AWE was really an API that was built back in the 32-bit days. I know that sounds crazy. Anybody on the phone, they're like, was there such a thing as 32-bit processing? There was. That's originally why this technology was built. But it turns out it's actually faster to access memory this method, and it gives us this lock pages type functionality. And we're going to show in a demo and in some slides here, how can you tell if you're using lock pages? Along comes our team that does benchmarking and said, you know what? If you use the virtual alloc call with this option called mem large pages, it is also locked like AWE, but it has an interesting property. The size of the pages from a Windows perspective, and when I say pages, I don't mean database pages, I mean Windows pages that are in memory from a Windows perspective, they're larger in size. And we found out we could get a performance boost. So if you turn on trace flag 834 and you have this lock pages privilege, we will use this concept called large pages. And here's the thing that's interesting about it. we allocate the memory up front if you use large pages. So if you use large pages, we're going to allocate this memory up front, and that can be an interesting scenario for you because it could take a while to allocate memory. So if you set max server memory even at 0, or you set max server memory to a very large number, we have to allocate all that stuff up front as we start the engine. We've seen people have issues with that in like a cluster failover scenario. We typically only recommend people use this large pages if you're really doing some fine-tuning benchmark scenarios. You may have different experiences here as you're watching this presentation where it's helped you or not. We use it for benchmarks like TPCH, and that's why we document the whole process. Recently, over the years, we've found that column store indexes has issues with this. So instead of 834, we have a different trace flag, 876, that if you're going to use column store and large pages, you want to use that trace flag. Okay, max server memory, just like max degree of parallelism, it's probably a religious war in the community about should you set this, should you not set this, what should you set this to? Let's just state some facts so you understand what it means. If you set it to 0, it means it's dynamic. In other words, the maximum is dynamic, but I got this from the source code. It is not the absolute amount of physical RAM. It's the minimum of 95% physical RAM or 50% of the available RAM left. I know that sounds like a complicated algorithm. What it really means is we are going to go almost the amount of physical RAM on your computer or virtual machine. But as you'll see here, we're going to talk about the fact that we could lower that value. And you need to get used to this term, these two terms. Max server memory will end up being something called the target or the ceiling to which SQL will not grow above. And many people choose on big servers for this to not be 0, and they'll set it somewhat less of physical RAM. It could take an entire presentation to describe like experimentations people have done to decide, well, how much should that be? And so I always tell somebody, if you're going to use locked pages, because then Windows can't trim us, you probably should set this not to 0. But you need to experiment with how much you should set this to where you leave enough memory for the operating system without causing any issues for the system. And then there's this concept called external pressure. So if we detect in SQL Server, and we can negotiate with the operating system actually, we get notified, hey, there's some memory pressure going on the computer you're running on. We call that external pressure. We can lower this ceiling or the target dynamically down. But it does not change the configured value. So we can lower that ceiling, but we can go back to that ceiling if we need to, if this pressure has gone. Now, min server memory is the floor. Think of that as the floor to which SQL will not shrink below. We do not allocate this at startup, and a lot of people have asked me, what should I set this to? So on a machine where you have a standalone SQL server, and that's the only thing running, I just leave it alone. You may decide, though, on a server we have multiple instances to set this differently. And in fact, speaking of multiple instances, here's something that people don't know about. If you put multiple SQL Server instances on a computer, they do not know about each other from the perspective of memory negotiation. So it's not like one SQL Server says, oh, your max server memory is at 8 gig. I'm going to adjust mine dynamically because you might need 8 gig. We don't know about each other. The same thing you're going to see applies for containers. So that's another scenario where you might start playing with what these are the appropriate values for your system in a multi-instance environment. Now let's make sure we kind of bust some myths about what locked means. The locked pages memory model is, again, a scenario where we're going to use APIs so Windows won't page that memory because it's not part of the working set. But notice this comment here. Other memory, like thread stacks and even Windows heaps, can be trimmed. And in fact, as it turns out, some memory, even when we're using locked pages, SQL Server doesn't use AW APIs. It's a very small amount, but it does in some cases not always use that. So there is a small amount of memory, including thread stacks, that could be trimmed even if we're using locked pages. So I've had some people tell me, well, I use locked pages, and then this working set trim scenario occurred because I saw this in Perfmon, and I had a performance problem. And I'm like, yeah, our thread stacks got trimmed. I mean, the actual stack memory for a thread, if that gets out into page file, for SQL to have to read that back in to execute code on a thread, that could actually be a performance problem. So when you run into these working set trim type issues, you have to go look and see what's going on in the system. Are there other things running on the system that could be causing issues? And again, large pages are also locked. Now, what is the difference between a locked page memory model and SQL locking memory? So what that means is that we have max and min values of our ceiling and our floor that are independent of that lock model. So whether using the conventional model, the large model or the locked model, SQL's max server memory ceiling and min server memory floor are independent of that. We don't pay attention to what that model is to make decisions on the target or the ceiling. Remember, the target or the ceiling is a response. We lower that if the operating system says there's pressure in the system. And then min server memory, if we start lowering that ceiling down, of course, think about a concept of a room. You can't have your ceiling below your floor. We will never do that. We will never allow memory to go below that floor level. So I thought this was important for you to understand, because I've had some people, and it's not your fault, it's a complex topic, say, well, I've got the locked pages memory model on, and therefore my target won't change. And I'm like, no, that's not true. The ceiling or the target of SQL Server memory, that is independent of whether you're using this locked model. This locked model is purely used to avoid Windows from taking any of our memory and writing it out to the page file and trimming our working set. Okay, let's look at an example, and we're also going to go do a demo to look at this. This is like a perfmon chart where you see target memory here, total memory, and private bytes, which is the amount of memory being allocated to the SQL Server process. So first of all, total server memory right after startup is fairly low. In this case, in my example, it's like 500 gig, right? That's the total server memory. Whoops. Now, the ceiling, in this particular case, I've set, let's assume, max server memory to 1 gig. So you can see the difference here. The black line is my total, and the red line is my ceiling. So I can grow dynamically within that. And in fact, if a query starts and starts loading pages, you'll see the black line start running and moving up towards the red line. Now, funny quick side story is, in the early days of SQL Server on Windows NT, and being in SQL support, I often had to work with the Windows support team on cases, on issues. And I'm not making the story up, this is a true story. In those early days, we're talking about like mid-90s, right? The Windows support team would walk up to my desk, we were a pretty small team back then, and say, Bob, we've got another SQL Server memory leak going on. And I'm like, SQL Server memory leak? What are you talking about? And they would show me a chart like this. And then say, yeah, look at that black line. Do you see how SQL's memory is going up and climbing? That's a memory leak. And I'm like, no, that's what we do. That's how SQL is a hog. As soon as we start using memory, we are going to start climbing and climbing. And so I'll tell this engineer from support team Windows, did we ever back off? Did we ever peak? And they're like, yeah, it's weird. You guys were climbing, and then it kind of leveled off. Like the leak stopped. I'm like, no. That is us doing the following. So when the query is still running and loading pages, but we hit near this ceiling, we hit a concept called internal pressure. And SQL Server has mechanism in internal pressure scenario to tell all the caches in the system. It's a kind of notification system. Hey, caches, we are running out of memory within the SQL memory system. Everybody needs to start flushing their caches out. So what happens in the case of buffer pool? If the query is still running, we're going to start throwing away pages that are free, that are not dirty, right? And loading in pages we need to finish our query. Or if they're dirty, in this case, we're just running one query here, they're not dirty, I might need to write them at the disk. So internal pressure causes all the caches to start adjusting. But remember now, the fixed memory, they can't adjust. So there could be problems if the ceiling gets lowered, and we'll see that in a second here. Okay, so let's say external memory pressure kicks in, or I change the ceiling with max server memory, and I drop it to the floor, which in this case, I've set the minimum to 512. You see how now the black line starts dropping. So the total server memory is going to start falling down towards that ceiling, right? Because we can't go above that ceiling, but we can't go below the floor. So if we hit this kind of type scenario and we need fixed memory, we could run into some problems. But notice here that the black line and the red line are right on top of each other. Okay, so if the query is still running during this dropping scenario, what is going to happen? Like you may be asking yourself, does the query fail? Nope, doesn't fail. It just means you got bad performance because we're having to throw pages in and out of cache. Remember, we still need pages probably from disk to be pulled into cache. So pages that we previously read are getting thrown out of cache. It's kind of a crazy, we call this cache sloshing in some cases. So if the query completes right here, let's say it's done at this time level, and the pressure goes away, notice that the ceiling goes back up. But the black line does not go back up. Why? Well, we don't need any memory at that point. So you can literally have this dynamic scenario where the target or the ceiling can dynamically adjust itself back up, But if you don't need any memory, we won't grow our memory back until we actually need it. Now, the other thing to notice here is that private bytes will always be slightly higher. And if you ever saw this private byte line start really climbing way above our total server memory, you truly might have a leak in SQL Server, but not from the SQL Server code. You'd be having this probably in something else. Okay, let me just see something here real quick. Okay, so let's look at some accounting data. So number one, SQL Server often is seen from Task Manager. People in Windows will look at this all the time, and they'll look at something called working set and something called commit size. Now, another thing to look at is a DMV called OS process memory. So let's kind of tie some things together. The working set is often tied to this physical memory and use KB, but remember this, large and locked pages are not part of the working set. So this physical memory counter is a combination of all three. So if you're trying to tie memory accounting together, like, hey, this working set's really low, what's going on? Well, remember, large and locked, which we account for inside SQL Server, are a combination of all of that. So when you're trying to tie this together, you got to keep that in mind. Second of all, the commit size should line up. We have virtual address space committed. So if you're looking at commit size, which again is a kind of a combination of these things plus additional memory, that's going to line up to this DMV counter. And remember, this is something you may not be aware of, but even without that trace flag, we can use large pages internally, not a large amount, not for the buffer pool and so forth, but for small overhead, we could potentially use large pages. So that could show up if the log pages memory privilege is turned on. Now, some of you may have seen and heard about this old DBCC command called memory status. I find it somewhat useful in some cases, especially for NUMA scenarios. I still use it in some situations, but I wanted to kind of line up some things here. So first of all, notice that the lock pages and large pages tie into these two DMV columns. And then also notice that DMOSSYSINFO, this is a very common DMV used, and I like to use this one because if I'm not looking at perfmon, I can easily see what is my total and target. And what I mean by that is current committed lines up here, target lines up here, and here's how they line up to perfmon. So you can see here that committed KB will be my total and target will be my ceiling. Now just a quick comment about this. People have said to me before, Bob, we're not using enough memory. SQL Server is not using the amount of memory it should. Or SQL Server is having a performance problem because memory is, under huge pressure. I get those kind of type questions. What are the first two things I ask anybody is show me these two numbers. What's the target and what's the total? Why do I want to see target? Because if target is really low, that means somebody either used max server memory to change it or there was pressure in the system. And there's DMVs through ring buffers and stuff for us to find out if there was pressure. So if anybody ever asks you, hey, is SQL using the memory it should? Or is there something going on with pressure on your system? Always start with target and total to find out the ceiling, the usage, and then of course you would look at min server memory to see what the floor is, which typically, again, you may not change. But keep those two important counters in mind. Okay, so let's definitely do a demo. Let's do a couple of fun demos too. Let's see, what do we got here? So I've got a perfmon on my local laptop right now. Now I threw up page life expectancy, which is a counter a lot of people use to look at buffer pool. And you notice here it's really large because I've been running the SQL Server for a while. I've had this run all night basically. And you can see here my total is around like 800 meg and my target though is like 4 gig because I've set max server memory accordingly. And my private bytes is slightly above it. Notice that's the green line above the total and the ceiling is my red line. So let's go over here and let's go run. Let's look at a couple of queries. So under Management Studio, here's some DMVs. Remember this is committed and committed target. So let's go run this and see what we got. Okay, can you see here that these two numbers are lining up to perfmon? You can see how those kind of, like we talked about, how you line those up. This is the total physical memory. Remember, if you get down here to physical memory in use, this is the working set plus this together to give you that total number. That's really how much physical memory SQL is literally using on this system. And then one thing that we did not talk about yet is memory clerks, which I'll show you in a debugger example in a second. A clerk, think of this way as a categorization for accounting. And you'll notice here when I'm looking at these clerks, I'm looking at pages KB, virtual memory KB, and AW allocated KB as the sum. I know that sounds crazy, but as it turns out, from an allocation point of view, these various clerks, which I'll scroll up, you can see here in a second, these different clerk systems may use 3 different ways of allocating memory, not always just locked pages. So let's run this and see what that looks like. So this is a way to find out what are the top memory consumers. And remember my diagram of the caches and the fixed memory and stuff? At a detail level, what are the top consumers in my SQL system? And so you notice here at the very top is the lock manager. That's interesting. I've actually not run a lot of queries to load pages, so that's not totally unusual. That's fixed memory, by the way, that lock manager. The buffer pool is what you expect. This is across my system, my buffer pool. Then look at something like XTP. That's like heckaton memory. I even got CLR memory. You can look down here and find like this is procedure cache. This is part of procedure cache. A lot of these different things are fixed, and a lot of these things, some of these things are caches. This is just a way for you to get a perspective of what are the consumers running around on my system. All right, let's try an example here. Let's go back and look at perfmon. So this is perfmon. Let's run a query that's going to go up to that ceiling. Let's come back here. So I've got this database called Go Cowboys, and there's no way anybody is allowed on this call to criticize my sports team's names, especially Anthony. He's not allowed to do that, or I may drop the call at any point in time. So I'm going to run my query here and try to load up some pages and see what happens. So you'll notice here that, here we go. Now notice my total, now in this particular case, my total server memory is above my target. Notice here, it's actually right around the same, but because of the way I've got this set up, it looks, oh, sorry, private bytes is, sorry. So here's private bytes. Okay, this is the part that's funny. I forgot about this last night when I was running this. I looked at this and I saw the green above the red, and I said, wait a minute, did total go above target? In this particular case, because of the way perfmon looks here, the total and the target are right almost on top of each other. Notice the total is just below that target line, so you don't even see the blue. Like you can't even tell that the blue is there, right? But really they're right next to each other. Now the private bytes though, as I said, is slightly above that, and it always will be. Notice what happened to page life expectancy. Oh my goodness, it was like 48,000, it went down to like 48. That's because as I started loading buffers into cache, the server realized because I'm so squeezed on my ceiling, my page life expectancy is not all that great at this point. Well, let's have some fun here. Let's go over here and let's change some stuff. Let's go lower the ceiling by changing max server memory and see what happens. Let's go down. And now you're running and you're like, well, Bob, you just made a change. How come it doesn't take effect immediately? This is because one of our background threads called the resource manager is polling and looking at that change to that value periodically. So it's not an immediate change, but notice within seconds this changed. And what happened to our system? Notice here the red line, which is the ceiling, went down, and the blue line, which is total, went down with it. And notice page life expectancy dropped down to 0 at this point. Like I don't expect anything to stay around in cache. But private bytes remain slightly above this. So you can see, can you see here the blue line is just a little bit right under that red line right there. And then here is our private bytes and page life expectancy. Now, if I go back to running my query again, and I set this back up to the ceiling, you can go back under perfmon, and you're going to see what's going to happen. Just like we talked about, you expect the red line to go back up, but the blue line, all of a sudden, we're going to be able to see the blue line now because the total, I'm not using it. So you can see our ceiling's back up again, and then notice the private bytes is slightly above that value. So let's have fun with another scenario. I always, in my support days, love breaking SQL Server. So here is a VM. I've got an Azure running SQL Server. I don't want to break my laptop, so I'll just go break a VM in Azure, a SQL VM in Azure. Now right here, if you'll notice, in my perfmon, my total is about 300 meg, and my target is about 12 gig because I've got max server memory set to 0. So let's have some fun. Let's go set max server memory to the lowest possible value, which is 128 meg, and see what happens. So let's click that. That ran for me. And what would you expect to happen here? My total server memory is 329 meg. My target, here goes down to 128. And look at this behavior. This is the one scenario you're going to see where the total is above the target. Why is that? That's because that total memory of 269 meg is fixed memory. We have squeezed all our caches down. Everybody's tried to relieve pressure in the system, getting rid of everything that can be into the backing store, and fixed memory is still around. So no problem. I think I'll go fix this. So I'll run spconfigure to go back and I click it, and uh-oh, I'm out of memory. Now, why am I out of memory? Because we are so starved of fixed memory. And remember, we set the ceiling down, so we can't grow. So we don't have enough memory to even run a query. And if you go to your error log here, you will find that happens. So let's go type out the error log. Actually, let's do it this way. Let's go look at the error log for Notepad and see what happened. This is an out-of-memory condition in SQL Server. It looks something like that. You'll see that 711 error, and then you'll notice here that I start getting a dump of what memory status looks like. So DBC's memory status is almost dumped out to the error log. So when somebody ever gets one of these errors, I start looking at some of these values like, what's going on here? I got a lot of available physical memory. That's not the problem. But notice here, I can see right away this problem right here. I can see my current committed and my target, and that is a bad problem right there. So why would that happen? Well, I obviously adjusted max server memory too low that it can possibly be, but external memory pressure could kick in this case if it was really a bad server and cause a similar type situation. So you're thinking to yourself, how do you get out of this thing? You can't even stop the service in this case, so I brought up this. So I'm gonna go kill SQL Server. Let's go in the task there. And then I'll do a little trick. So the trick is I want to start up SQL Server in single user mode, also with this -f trace flag right here, -f trace flag for what's called minimal configuration mode. This is going to let SQL Server use default configure values regardless of what's in SP configure stored. So it's going to use max server memory at 0 to start the server. And I'm going to use -m to tell it, let me get in there with Management Studio. So I'm going to run this. Whoops. I got to be in the right directory. Let's go here. So you see the server is starting up, and then I get to come in here, and I will go to say file, maybe new query. Is this going to work? And it will. And I'm going to come in here, and I will run my query, and I fix the server. So then I can go and I can shut down SQL and get back up again. So there's your fun demo to how to break SQL Server. Let's do one last demo, because you have to have a session in this conference, I've heard, with a debugger. Somebody said that that's a requirement. So let's go back over here. Let's go to a command line of my local SQL Server. Let's see. Let's get rid of this guy to make things interesting. Let's get rid of him and him. Yeah, him as well. Okay, this is just the command line of SQL Server. Let's go ahead and stop SQL Server. This is on my laptop now. I'm back to the laptop where I was running SQL before. Okay, so then let's go do this. Let's go a debug session. And so you're asking yourself, like, what are you doing the debugger? Well, I'm going to run the Windows debugger. I'm going to load public symbols, and I'm going to use SQL Server from the command line. So let's do this. Okay, so here's my Windows debugger. What it's doing is the debugger is going to start up the SQL program, not attached to it. And I'd like to see how SQL uses APIs. So I thought you'd find this interesting. I'm going to show you this API. This is the API we use for AWE. Since we're a NUMA system, even if I'm not on a NUMA computer, we always use this API. And I know to set a breakpoint on this because we're using the kernel 32 library. Now this is the part that you don't know, that you have to just know, unfortunately, is that these are really mapped to a DLL called kernel base. So I'm going to set a breakpoint called kernel base, and let's go and pick that guy. This is the way we debug, guys. We just go out there and find the APIs, and we're going to set a breakpoint, and we're going to go. And boom, I've stopped. Now, the K command is going to give me a thread stack. So what is going on here? So first of all, this is us booting up SQL Server for SQL OS. So even SQL OS needs its own memory. So we're going to use the SQL OS systems. Notice I've got this memory clerk here, and then I'm going to come up here, and I've got something called a block allocator with an SOS. And if I scroll up, eventually what's going to happen is that even SQL OS itself needs to use this API call. That's kind of like our own API call, but then directly calling the kernel call. So we're actually going and allocating physical memory at startup. Much of the memory at startup is going to be fixed memory. So let's go again. That one's not interesting. Let's see. Let's find one that's interesting here. I was going to show you this one. We're starting to create a cache store here. This is a good one. So many of you are programmers, know the new operator in C++. This is us. We create our own new operator. We overload the new operator, our code, and the new operator results in all of this code right here. All of this code right here is the new operator calling all of our code to ends up allocating memory within the APIs. Let's see, one more. Lock monitor. This is the one I wanted you to see. Look at this one. This is us loading SQL CLR, so we're calling into CLR. Notice that, right? This is literally the CLR code. So the CLR code comes along and says, hey, I need some memory. I need to allocate memory. Well, we've got it hooked into SQL CLR so that it calls back into SQL Server to get memory, to call SQL OS, to call memory within the operating system. So this is how SQL CLR routines allocate memory. It's a callback system where we've registered with SQL CLR, so all of it's controlled by SQL OS. So there you go. This way now you can go along and say that Bob Ward did bring up debugger. Maybe not as sophisticated as say Argenis is going to do. He's probably going to do a lot more sophisticated debugging sessions, but that's my debugger of the day. So let me stop for a second. Hamish and Reed, got any kind of crazy questions out there before I keep trucking?
Yeah, I have a couple of questions. Thanks, Bob.
Okay. Yeah.
Question here. What happens internally when min and max memory are both the same? Dynamic memory won't work then?
Yeah, no, dynamically, so if you set min and max the same, it is fixed at that point, right? So if you set this, if you set max at 4 gig and you set min at 4 gig, first of all, we don't allocate min up front, okay? So when you start the server and min is at 4 gig, we don't just jump to 4 gig. Now, large pages is different. We allocate max at the beginning. So it is true, though, that once we get up to the max, right, we get up to the 4 gig range, if you've got min set that and we get pressure in the system, remember the external memory pressure, we don't drop below min. So once we grow to that max level and min is the same, we will stay at that level. But by the way, that could cause all sorts of problems. Not sure I recommend people immediately going into that mode, but that's kind of how it behaves.
Nice. What are the situations where you would not recommend granting lock pages in memory? What are the situations you would not recommend it?
You know, to be honest with you, I just always use it. Now, somebody, this is really interesting debate. There's even debate in the SQL engineering team about this some. So we don't do that in Azure today, by the way. We don't by default do that because we have not seen working set trim problems occur in Azure. You know, when I'm talking for the people that built SQL OS, using AW APIs can actually be a little bit faster than using normal virtual alloc APIs. So, you know, I guess the problems I have seen in some cases is people set locked pages and they didn't set a max server memory value. And then Windows started having problems because we use so much memory that Windows can't trim out. So the pure Windows person may say that you shouldn't be doing that because we can't properly kick in our trimming algorithms. Man, if I was running a production SQL server, I would definitely go take a look at putting this thing on because I have seen working set trim issues occur with Windows where plenty of physical memory is available. It is fair, though, that if you're going to use locked pages, I would set a max server memory value that is not 0. I would try to find a value that's slightly below physical memory, maybe 1 or 2 gig, and experiment with that to see whether I don't want to waste too much memory. But my personal experience, when customers would call me in support and they'd have issues, I'd say turn it on.
Awesome. Would the Windows paging still take place even if you have locked pages and memory option configured?
The answer is yes. We talked a little bit about that. So Windows paging happens, period, for any process, okay? So let's say you have a scenario where you have locked pages turned on, the privilege is set, and SQL is using locked pages. So absolutely 100% Windows can page the SQL. It looks at SQL Server as a process, says, I'm going to do some paging. So what does it do? Well, it looks at the working set of a process to do its paging. And so in this particular case, if SQL is using locked pages, the pages that we use for locked, which is like buffer poolant, for example, Windows cannot page them because it's not part of the working set. Windows can only page memory that's part of a working set. So, however, there is other certain amounts of memory that Windows can page out, like thread stacks, and there's a small amount of fixed memory that we allocate with virtual alloc and other APIs that could be paged out. So yes, Windows can do paging for SQL Server, even with locked pages, but what's not going to get paged out are really important pieces of memory like the buffer pool and plan cache, etc.
Awesome. What about setting a fixed size, i.e. 4 gigabytes, for the page file? Is this a good practice?
As far as the Windows page file goes? Is that what the question is? Yeah.
Yep.
Yeah, I would use the guidelines that Windows has set up for paging. Linux is the same way. First of all, make sure you have a page file and then put it on the appropriate disk. So Windows has guidelines out there about what should the size of the page file is, and it's usually a factor of how much physical memory you have on the machine. So go look at the guidelines for Windows. It's been a while since I've looked at that, but that should not be a SQL Server decision. That's a decision for just running a Windows Server, period, independent of SQL Server.
Okay. Excellent. Do you want me to keep going? We've got a few questions. Some of them relate to Linux and Azure. So
Linux and Azure, let's hold those off because I still have some slides on those. Now, how long do I have till?
Another
20 minutes?
Yeah.
20 minutes? Yeah.
You have 30 minutes. You go until 10:35 Eastern, and it's 10:06.
Look at Ree. She's all over it. So yeah, let's if there's any other questions, let's answer them. Sure.
Okay, sure. Can you explain something about the flush cache logs and the SQL error logs? Why is it happening?
Oh, so somebody's seeing like flush cache occurring. Yes.
Yeah.
I have seen that before. There's a couple of reasons why that might occur. One is pressure that's occurred in the system. Another is, and I think I may have this on a slide, I don't remember, as it turns out, there actually are some commands you can run like alter database or spconfigure where we'll go flush the procedure cache. So if it's the same message I'm thinking of, those are probably those situations that are happening. If you're seeing that every once in a while, I wouldn't worry too much about it. But if you see it consistently, you need to go see whether you're running a certain set of commands that cause it or whether there is pressure going on in the system.
Bob, I wanted to quickly say Erin Stellato, who presents next, said you can go a little bit over, that she doesn't mind.
Well, that would be typical of a Cleveland Browns fan.
Well,
to say that. That would
you know
be
what?
normal.
She takes it back. You have to end right at 10:35.
Well, that's the Cleveland Indians fan in her now saying that. So. Any other questions, and then I'll keep trucking.
Yeah, sure. I see a lot of open connections on my server. Will that hurt memory? And what is the best practice to close connections?
Well, first of all, if you're worried about connections overall, about open connections, make sure you're using connection pooling for apps that make sense for those scenarios. Connection memory is very small. So if you've got a large amount of memory in your SQL Server, connection memory should not be chewing up a lot of memory on your system. However, there are scenarios where you can cause memory leaks with SQL Server by keeping things open. So I've seen one scenario I used to see, not as much anymore, but cursors, like server cursors. If you open up a server cursor and you don't close that cursor, we have to keep that memory open, and that's fixed memory because we can't flush a cursor to disk or something, right? So connections in general shouldn't be an issue. It might be indicative, though, of some other problems by leaving a connection open. So look at connection pooling, but a single connection does not require that much memory, but it is fixed memory. So if we're under a really severe memory pressure trim, we can't flush that out. There's no way to, there's no cache for connection memory, right? To write it at the disk. So.
Yeah, awesome. Can large query memory grants cause internal memory pressure in SQL Server? And where are the query memory grants allocated from?
I'll address that in an upcoming slide. Okay,
cool.
You want to truck on a little bit, and then we'll have time at the end. We'll have time at the end for sure.
Thanks, Mike.
Based on what I got left. I just love it when I get called mate. I just love y'all's way you speak and mate. I love that. Okay, here we go. Other memory topics. So first of all, buffer pool logistics. We showed you about page life expectancy. There's some quirks there. You should kind of look. The community's spoken a lot about whether that's good or not good to look at. It is still good to look at. You saw in my example where page life expectancy, which is a rate that we have, right? It dropped to almost nothing. And that was because of pressure in my system. But what are other signs of maybe I don't have enough buffer pool? If you see a consistent set of page IO latch waits happening all the time. Remember, when we first load pages from disk, this is normal. A page IO latch wait is normal, period, because this is just an indication of the time it takes us to wait for a page to be loaded from a disk drive. So don't think that the presence of a page IO latch wait is bad, but if you see them all the time and the waits are long, you probably need to go look at something. And then drop clean buffers is an interesting one. This is not intended to be used in production, okay? But I use this all the time to force pages to be loaded from disk. So when you run this command, we'll take any database page that is not dirty and free it up, basically, for memory. So then next time that you run a query, we would load that page from disk. So if you're out there wanting to test how fast can I load my database pages from disk, you would run this command on your database and then run your query again, and you would see IO latch waits kick in. So what about NUMA? NUMA is a commonly used, obviously, technology across major servers. And you should know we could spend an entire hour talking about SQL NUMA and how it works. And shameless kind of plug, but if you want to go back on that SharePoint, the site I have, ak.ms/bobwordms, which I'll put that up at the end. Or if you can go back and find my past talks where I've talked about internal memories, which I can't remember what year that was, but I get deep into this topic. So NUMA, you need to know that one of the things about NUMA you want to do is make sure that on a NUMA machine, when you allocate memory from the local node. And so that's our goal in NUMA, which is why if you're looking at memory accounting across NUMA nodes with SQL Server, you may not be balanced because we're going to try as much as possible to use local node memory if we can. The other thing you should know, though, is that local node page allocation is not a guarantee of local node access. What am I talking about? Like buffer pool. You know, buffer pool is spread across the entire instance. So it's possible for somebody to allocate memory for the buffer pool itself on a given NUMA node, but somebody else access that memory on a different node. There's not much you can do about that, right? But some memory is partitioned based on NUMA nodes for performance. And we had this problem a long time ago with something called memory objects you may have run into before. Mem objects is what we call them. And so we, along the releases of SQL Server, went along and we automatically handle this now. We partition these objects, which is typically for things like fixed memory, like the case somebody asked about memory grants. We partition these per NUMA node, so they're allocated and used on a given node, and it really has sped up performance, and not just sped up performance because you're using NUMA, but because these memory objects are typically, in some cases, shared. So if somebody creates a memory object and then multiple threads need to access it, and then if it's partitioned by NUMA node, then of course it's much faster access and it's the performance is spread out. Let's talk about grants for a second. So memory grants are memory that are fixed memory. There's no backing for this, right? And we allocate this at the start of query execution. And we determine if we need a grant for things like sort memory or hashes. Let's talk about a sort for a second. If you were a computer programmer and you had to sort data, you're going to have to allocate a memory buffer like a linked list or an array in your code to do the sort. Let's say you're reading it from a file. You want to read from a file and you want to sort that data. Well, what you're going to do typically is allocate memory and then sort the data in memory. Same thing for SQL Server. If we're going to do a sort operator, we're going to allocate memory to do the sort. A hash join has the same type of process. We need a hash table. We're going to allocate memory for it. That's why we need a memory grant. And that memory is going to be decided at the start of query execution based on the plan. Well, the problem is this. If the estimates in the plan to feed these operators, like sorts and hashes, if the estimates are too low from what's really needed, we might have a problem. Houston, there's a problem. So let's say that the memory for a sort, the estimate is like 1 row. So we allocate a memory grant for a sort of 1 row, which is more than one, it's not like a byte or something. But let's say all of a sudden we come to actually do the sort and it takes 1 million rows. Well, we have memory for the sort, but we don't have enough of it. We cannot dynamically grow that memory grant. So what we have to do is we have to use tempdb as a backing store for the sort memory. And we call that a sort spill, which results in poor performance. What about the other direction? What if the estimates are wrong feeding that operator? So we think we need to sort 1 billion rows and we only sort 1 row. Well, guess what? If these memory grants are too large, it can result in some bad behaviors like resource semaphore waits or plan cache eviction, which is kind of what that question was about. So these grants get too big, we have to actually take memory from other places, and plan cache is actually one of those, or if there's too many of these, you can get waiting scenarios. So what do you do about it? Well, first of all, in many cases, there's an opportunity to go look at the plan to find out a problem with estimates in the plan. But from an overall server perspective, resource governor can be used to limit the total amount of grants on the server. And one of the problems that we had with resource governor up until SQL 19 is it was a percentage number that only supported 1% or greater. So on a 1 terabyte system, that's still a lot of memory. So resource governor now, resource governor now supports values less than 1%. The other thing we did in SQL 17 and 19 is we adopted a mechanism through intelligent query processing where you change your compatibility of your database. And we now can try to go take feedback from the query and change the grant the next time. So I said it's fixed memory allocated at startup. If we allocate that memory at startup and then we finish the query, we know if it was too low or too high at the end of the query. So what we can do in cache is we can adjust that value for the next time the query runs and avoid these too low or too high scenarios. That's called memory grant feedback. It doesn't change the estimated problem, but it actually can fix the symptom of the problem, which is a poor grant, which leads to, as you see in these cases, performance problems. So what about memory leaks? I showed you an example of a memory out-of-memory condition in SQL Server. So SQL Server itself manages all its memory. So if there was a leak within the SQL Server memory itself, let's say one of the developers that were doing memory grants, they own that code, they were leaking memory grant memory. Well, what would happen? What would happen is you'd get out-of-memory errors in SQL Server and potentially this kind of message 701. Why is that? Because that is fixed memory that doesn't go away and cannot be paged out. And so if remember that box I showed in the beginning where that gray thing was called fixed memory? If that thing is huge in your server, we can't shrink that. So if memory pressure kicks in, we all of a sudden can't get access memory for other fixed memory operations. So a memory leak within SQL Server is going to look like that. A external code leak, like let's say there was a DLL loaded in SQL Server that's not part of the SQL memory management system, that would look like a private byte leak. This is where you see that private byte leak line go way above the SQL Server total server memory. That would cause problems maybe within the Windows operating system itself, and that could generate external memory pressure or even eventually issues with the operating system. So unless there was a leak within the SQL OS allocator code, an actual private byte leak would be somebody else's code that's causing the problem. And by the way, on this memory leak for SQL Server, I mentioned one example where you could cause the leak that's not a bug, and that is opening up like a server cursor where you never close the cursor, because that's fixed memory that we cannot cache out. Okay, so let's talk about plan cache eviction, because this is a major performance impact that can happen. The buffer pool is a little more important, obviously, but it gets more memory than plan cache. So first of all, if memory pressure occurs because we're hitting that target, okay, and let's say external pressure occurs, or a large memory, let's say one of these three scenarios occurs. It's internal pressure because we're hitting the target, external pressure occurs, so we have to lower the target, which could result in internal pressure, or you get these large grants. That's going to cause us to go in and evict caches from plan cache, which is going to cause performance problems because what happens? We have to go back and load and recompile your query and put it back into cache. There is something called a clock hand in DMVs you can look at. Think of like a clock where we move a hand of a clock, and then eventually when it hits a certain number, we take an operation. So these memory pressure scenarios will cause the external clock hand to move for a given cache entry. And when it moves so many increments, then when we evict something from cache. So an internal clock hand, though, is a cap limit. So independent of these pressure problems, we cap the plan cache. There's a certain cap to it. And we don't allow it to be unlimited. So when you hit a cap limit, we call that an internal clock hand problem. So these DMVs will let you look at a given cache system and say, am I seeing a lot of movement of the external clock or the internal clock? So cache limits are more scenarios where maybe you're not being very smart about your cache, like a lot of ad hoc queries that are kept around in cache versus using stored procedures or something of that nature. And there's all this concept called cache wars, where we have other caching systems that are being used in SQL Server that could cause us to compete for this cache limit. So internal clock hand for cap limits and external clock hand for pressure. This is very important for you because if you're getting a lot of planned cache eviction, you got to figure out which one of these problems am I running into so you can then accordingly take action. And then you asked about things in the error log. You might have caused this. Certain DBCC commands could cause us to flush the cache, obviously. There's also versions of this now per database. And some SP configure changes require us to do this. We've got those documented. You could be actually causing us to flush out the cache or to cause planned cache eviction. And then again, are you smart with what you cache? So I've had some people say, hey, Bob, I'm getting planned cache eviction. I'm hitting these cap limits. This is a problem for me. And I'm like, okay, well, what are you caching? And they're like, what do you mean, what am I caching? I'm like, well, do you have a lot of ad hoc queries that are getting kept into cache, or are you being smart with what you cache? There is also, I don't list it here in this slide, but we do have documented some trace flag you can use to actually up this cap limit. You can actually make changes and kind of slightly increase it if that is a problem for you. Okay, let's pivot now and talk a little bit about some containers, Kubernetes, and Azure, and then we'll finish with some questions. So first of all, SQL Server on Linux. So if you haven't heard about this or seen us talk about this, I wrote a book on it. A lot of people like Anthony and others in the community have blogged about it and talked about it. SQL Server Engine on Linux behaves the same as Windows. And what I mean by that is that the SQL Server Engine code is the Windows code inside Linux process. We use a concept called the SQL PAL. And remember the allocate API I showed you? We still use those APIs in the engine. What happens is the SQL PAL is allowed to trap those, not emulate them, but trap them and turn them into actual Linux kernel calls to allocate memory. So the engine itself, from a max server memory, from a ceiling, target, all that stuff, it behaves exactly the same as Windows. What the SQL PAL will do, which is again, it's kind of, think of it as hurting the Linux process, is it uses a memory limit to expose to the SQL engine its maximum memory possible. So if you think about this, the memory limit MB, which is default, 80% of physical, that is think of that as the operating system version of the SQL engine to see what it can go to. And you can adjust this. If you want to, there's a configuration value for to change what is there. The lock pages concept is not applicable in Linux, but it can swap memory. So what we've run into in Linux, different than Windows, instead of working set trim problems, which again, it can do some swapping. But what happens in these extreme memory scenarios is this, the OOM killer. That sounds like a serial movie. It sounds like a movie, doesn't it? The OOM killer. So what happens in Linux is sometimes when Linux sees memory pressure issues in the operating system, it will terminate a process. Literally, it'll just kill a process. And that can happen to the SQL Server process, which is why we've had in some cases with customers to adjust this value here to affect so these problems won't happen. And we've got a really nice article in the documentation about how to tune other kernel parameters for Linux for memory. So again, if you're on a Linux system, the SQL Server behavior is the same for the engine, but you may adjust this memory limit MB depending on the configuration of what you're going to run on the system. What about containers? Well, right now we only support SQL Server Linux containers in production. So configuring the right amount of memory for container runtimes that require VMs is kind of important. Containers by default get access to all the memory in the virtual machine or the physical server. By default, imagine a SQL container behaving just like Linux here. That's exactly what it's going to do. It's going to run just like this by default. And these containers don't know about each other. So think about like the multi-instance scenario. If you've got multiple SQL Linux containers, now here's the part that's interesting. You can go in and take a container runtime like Docker and hear me?
Bob, you kind of drifted in and out for just a little bit there.
Yeah, I got some sort of message saying my internet connection was unstable, but I've got great connectivity, so I don't know if it's yeah, but are you guys now? Can you hear me all right?
Yes.
Okay, where should I pick up from just talking about here a little bit? What was the last thing you heard me say, Ree?
I don't remember.
It was like, what did you just say,
You talked about containers, so maybe like line 2 of your SQL Server.
Yeah, I'll just start over from this part here. So
Okay.
let me just start over. So first of all, containers are like SQL Linux.
Bob,
going to behave like a SQL Server Linux with this upper.
Bob, you were drifting in and out again.
They don't cooperate with each other. They don't know about each other. Now, you can configure Docker or other container runtimes to limit the amount of memory a container process gets. But guess what? We don't know what that looks like. The SQL PAL code and SQL Server don't know how to recognize a container runtime limit threshold because this is the way it works. It's really weird. If you set a container runtime memory limit, the container gets all the access to the memory, but if it hits the limit, the container runtime will kill the process. So I do not recommend you use container runtime memory limitations. You should use SQL Server to limit the amount of memory you need in a containerized environment. Same thing for Kubernetes. Anthony is one that brought my attention to this back last year. Kubernetes, you configure the amount of memory for a given node in Kubernetes, okay? SQL Server is not aware of Kubernetes policies for eviction. So like what can happen in Kubernetes is you can have a pod running with a container and Kubernetes gets low on memory and it'll take that pod and move it to another node. It's almost like shutting SQL down and moving the thing. Or if there's no other nodes, it'll just kill it. Well, we don't know about those policies. We haven't written our code to say, oh, let's go see if we're running in Kubernetes. Should we adjust our memory policies? So you need to configure the right amount of memory for your node. Excuse me. You need to configure the right amount of memory for your node, or make sure you use the SQL Server Linux configuration policies to adjust and run in that environment. So that's just a few little nuggets about Linux containers and Kubernetes. What about Azure? So first of all, for Azure Virtual Machine, it's the same as SQL Server. Remember, this is just you running in the Azure infrastructure. And so the guest operating system, whether it's Linux or Windows, take everything we've talked about today and just treat it the same way. Now, you should know, though, that you may be picking sizes for Azure VMs. And so something called the memory optimized sizes that you see out there, you have all these choices for sizes. There's a family type. You're going to get a higher CPU to memory ratio if you're choosing the sizes within Azure. What's more interesting is Azure Managed Instance. With Managed Instance, the memory limit is going to be fixed per vCore. So a given vCore option you pick for Managed Instance, you get a certain amount of memory per that vCore. And in-memory LTP is only available with the business critical choice for Managed Instance. Now here's the interesting part. We're going to see a demo in a second. The memory limit is enforced by a Windows job object. A Windows job object is not a scheduler concept in Windows. It is a concept in Windows where you can take a process and you can enforce resource usage on that process like memory, CPU, and affinity. So behind the scenes, we will use a Windows job object to enforce these memory limits because you don't know how we're installing a managed instance. You don't know the VM behind the scenes. We pick and choose that for you. So we may pick you to run on a VM, but we're going to enforce these limits that we've already established, right? So you might get access and see things from a SQL perspective that you have slightly more memory in your VM, but the memory limit's enforced by the job object for a process. A similar concept for Azure SQL Database. Now the memory limits are more scaled. It's not a fixed amount per vCore. It's more of a scaled number that the higher vCores you go, kind of the more memory you get. We'll still use Windows job objects, and you can even get up to 4 terabytes of memory with our new business critical M series hardware choices. Same thing, MMLTP is only with business critical. Now you got this thing with something called serverless. In serverless, you have a min and max for cores. And so what happens here is we have min and max for memory limits for serverless based on those choices. Now, how does this work? Well, serverless is all about auto-scaling and about pausing on idle scenarios. So in order to reclaim resources, if you're not using this serverless, something interesting, we may reclaim memory from your instance. And the way we do that is we're going to lower that ceiling on you. We're going to take that and we're going to treat it like an external memory pressure scenario because that's the only way for us to get memory back. If you go back and think about those diagrams, the only way for SQL Server to deallocate memory from the operating system is to lower the ceiling, right? To lower down the ceiling so that the usage of memory gets lowered. So if we lower the ceiling, the memory usage goes down. What does that mean? That means that in scenarios with serverless, when it's idle and you go back and use it again, we're going to have to warm back up the buffer pool cache and other types of caches. And then for hyperscale, the memory limits are the same as in a general purpose scenario. Today, but let me go look over at a VM I've got. Wait, that's not the right one. Let's go here. This is an Azure VM that's connected to both an Azure database and a managed instance. So for Azure Database, let's still look at this first. First of all, you have something called here. Let's see. Let's run this thing. That's going to show you some data like your CPU limits and so forth. Unfortunately, it doesn't show you this memory limit number. So you need to look at something called DMOS job object. It's a new DMV. Hey, Reed, can you hear me? Rita,
Yes,
okay?
I can.
Okay.
Yes, you do. You cut out for like a second or two, but you're good.
Yeah, it's really weird because my internet connectivity says on my side I'm really fine, but that's okay.
It's a Dallas thing. It's fine.
Ooh, oh my goodness. All right, so I may have to get on when Reed presents next time, and that's some fighting words. So DMOS job object is a new DMV for.
Hold on, Bob. You've gone quiet again. Bob?
How about now?
I can now.
Okay.
Yes, so you were out for about 10 seconds.
Well, I apologize to everybody online. You know, welcome to the world of running a massive virtual conference. All right. So,
and there's a whole lot of people in this session too. So
yeah. Well, hopefully everybody can still hear me okay.
Yes.
So just to reiterate, DMOS job object is a DMV special to Azure, and it's going to show you the true memory limit you get for Azure SQL Database. I also want to point out though that because Azure Database is running behind the scenes on a dedicated SQL instance for you, even though you don't see the instance, you still get access to things like memory clerks, so you still can dive into those kind of things. Now, this is Azure Managed Instance. Managed Instance is different. It's like a SQL Server instance, so you get to look at things like OS sysinfo and process memory. And notice here in OS sysinfo, it looks like you have like, I don't know, 46 gig of physical memory, but notice from DMOS job object, you only have 41 gig. This is an example of us using job object to limit, and again, it's not because we don't want you to get access to all the memory. It's just that we decide behind the scenes what VM infrastructure to put you in, and we need to enforce the limits that we've documented, so that's how we do that. In fact, in an error log, here's an error log entry for managed instance. You guys used to seeing that, like detected 46 gig of RAM. So I don't want you to get in these scenarios where you're looking at SQL instance level diagnostics, and you're like, hey, what's going on here? My Mac server memory, I can't get my target to that number. Well, that's because the target is going to use that number. So keep that in mind. The target or the ceiling is going to use this memory limit MB number, not that number when you're looking at your overall information. In fact, you can see that from OS sysinfo. So if you run OS sysinfo, you can see here that the committed target, that memory object number, and not to the physical memory that you see in the VM. Okay, so we got about 3 minutes left, and all I have left here is resources for you. We'll finish with a few questions. All the decks are here. I will put up the deck and any of the scripts I showed you. I'll put that up on the 8KB GitHub that those guys set up. This is kind of some interesting information. We do have some architecture information in our docs. People don't realize we have that. We talk about buffer pool and plan cache and lock pages and so forth. So go check that out. And then there's a really good article that the CSS team keeps up to date. These are recommended updates and configuration settings for all the different things, a lot of things we talked about today that they have experienced over the years that you should be using on your enterprise server. Okay, was that, I mean, people can give me all sorts of feedback they want. Hopefully that was somewhat 400 level. I don't know, Hamish, was that 400 level? Was that too low? I don't know.
So there are a couple of pieces of feedback that we got. The best slide ever on SQL Server memory that I've ever seen. 6 minutes in and I'm already learning stuff. So a lot of really positive comments. So yes, this was definitely a session. The session everybody expected from you.
Well, if anything was negative on there, I bet it's Argenis. I bet Argenis is sneaking in a comment like, this guy's terrible or something. That's probably what he did.
It's absolutely Argenis. You're correct.
It's got to be him. Absolutely. So.
Yeah. No, that was a great session. Thanks, Bob. The cool thing is I've written some notes to talk to a DBA on Friday, New Zealand time. So we were talking about memory stuff. And
nice.
So, yeah.
Any final Q&A you guys want to ask me before we wrap up?
Yeah, sure. Reed, do you have any questions on your side? Well, we're off the same page.
You and I are off the same Q&A. So Bob, there have been a couple of like lower level questions that I've tried to take care of before we get here, so to make sure you can get to the 400 and 500 level stuff. So I'll let our same questions. Hamish, go ahead.
Sure. What happens in Azure SQL when you do it? If you did hit out of memory condition, would you expect to trigger a failover yourself? Or how do you monitor memory in production for Azure SQL?
Yeah. So first of all, we detect outages like that. So those are like failure conditions where we're going to fail you over. And you got to remember that no matter what Azure SQL option you pick, now for VM, by the way, that's up to you. Okay. For Azure SQL Database or MI, we've got automatic things in the background to detect if your SQL server is not available. You got to remember, even a general purpose installation is almost like a failover cluster instance. We can fail you over to another node and get you up and running again. So in many cases, when there's some sort of condition causing you server issues, you don't attack it because we've already failed you over anyways. But you still can monitor your memory usage of things that we talked about. And remember, you can't lower the ceiling. So you can't change max server memory. So the only reason that you're going to start having some issues potentially is a leak within the SQL code, which we would then fail you over. In fact, we would go detect that and go fix that somewhere. Or there's just massive pressure. But remember, we control what runs on these servers now. So some of these scenarios I talked about in Azure are not even possible because we control what runs on them. So we monitor and make sure we don't have external pressure stuff going on. We control what else runs on the server, and then if you have some sort of failure condition, we're going to actually fail you over. So that's kind of the beauties of platform as a service, right? We kind of handle a lot of this stuff. Does that answer your question?
Sure does.
Yeah.
Thank you. Yeah. I'm just appreciative of the time.
Yes, thank you.
Yeah. So what I might do is just do one real quick last one.
Okay.
What is the best, quickest way to deal with resource semaphore in a live production SQL instance?
You need to go find out what the queries are doing. I've even seen resource semaphore waits occur because you just have way too many queries that have query plans with sorts and hashes, even if the grant is correct. So just go find out what the queries are doing. Then go look see at this memory grant problem. Like if they seem reasonable, go see if you've got a over memory grant issue. I will tell you that on SQL 19, with this memory grant feedback, I haven't anybody hit that because the feedback's kicking in and adjusting the memory. But if you do hit that, your choices are, of course, to go into Resource Governor and kind of control the amount of memory grants, or go fix the actual problem yourself.
Awesome. Well, thanks, Bob. I tell you what, it's
I'm going to stop sharing at this point, so let you guys kind of take back over.
This has been a wonderful session. It's definitely been worth staying up till 2:30 in the morning. Thank you so much.
Oh, Hamish, thanks for doing that. And thank you again for everybody on this call that's supporting this effort. And thanks all the organizers putting this together. We really appreciate it.
Thanks, Bob.
No, thank you very much, Bob.